let's have a quick review about definite integrals in one variable. Suppose you have the integration of some function f of x dx from, let's say, x is equal to x1 up to x is equal to x2. What does this really mean? The fundamental theorem of calculus tells us that if you have this function drawn like this, so you have some general function, this is f of x, and here you have x1, here you have x2. The fundamental theorem of calculus tells us that this integral really measures the area under this curve right here from x1 to x2. You could see the proof of this in calculus textbooks, but I'm only reviewing here. But as a concrete example, suppose we have the integral from 0 up to, let's say, 3 of the function x dx. Since you know how to evaluate an integral, you know that the result of this is equal to 1/2 multiplied by x squared. Then I will substitute from 0 up to 3. So I'll have 1/2 multiplied by 9 minus 0. So this is 9/2. If I want to draw this, I'll find that this function is actually a line having a slope equal to 1. So I can choose this color to be yellow, just like that. And here I have 0. Here I have 3. And of course, since f of x is equal to x, then the height right here is equal to 3. Then the fundamental theorem of calculus tells us that this integral right here is equal to the area of this triangle. So this triangle has an area of 1/2 multiplied by the base, which is 3, multiplied by the height, which is also 3. So this is really 9/2, just like the evaluated value for our definite integral. Very well, let's have a more detailed look at this theorem or this result right here. I am integrating from x1 to x2, from x equal x1 up to x equal x2, the function f of x dx. So this is again my function right here, and here is my x1, and here is my x2. Now this symbol right here is actually an elongated S standing for summation. So what the integration is really doing is partitioning this area right here into very small rectangles like that, and like that, and like that, and so on. Every rectangle of those has a width of, let's say, delta x and a height of f of x at one specific x. Of course, this is not a perfect rectangle because you have, let's say, this curve right here. So you have something like this, and like this. So this is not a perfect rectangle, but if you choose this delta x to be a very small quantity, then you could ignore this small triangle right here, because you'll have delta x multiplied here by, let's say, f of x. And if this delta x is very small, then you could ignore this small portion right here, and imagine that this is really only a rectangle. So what this is really telling you is the following. You are partitioning your area into very small rectangles. Every rectangle has a height of f of x and a width of dx. So dx is delta x. If delta x is very small, very small, this will be equal to dx. So here you are multiplying some height by some width, so you are getting an area, and then you are summing over all of those areas from x1 up to x2. If you sum all the areas of all of those small rectangles, you will get the whole area under this function or under this curve. So now we can say that the integration from x1 up to x2 of this function f of x dx is really a summation from x starts at x1 up to x starts at x2 of many areas. Let's call them ax, or a as a function of x. Every area of those is an area of some rectangle, and if you sum all of those areas together, you will get the complete area, which is equal to the value of this definite integral right here.